So today we're going to talk more on complex numbers and quaternions, only today we're going to approach this from the path of implementation, and that is implementing on a computer. So in my community section, I remember mentioning that I was a bit concerned about my convention because I found a video where a different convention was used such that the negative is in the upper right corner and the positive is in the lower left corner, whereas in the setup that I have, the positive is in the upper right corner and the negative is in the lower left corner. And the more I dug into it, the more that I realized that it doesn't really matter. In this video, he is taking the A and the B, and he's putting the negative, he's putting it in the row, and what I do is I take the A and the negative B and I put it in the column. Okay, so technically I'm transposed from this method, or this method is transposed from my method. Now there's a reason I do it this way. So what I'm going to do here in terms of code is I'm going to show you my setup. So when I call my function setup complex, okay, I put it in row, so it's row column. Okay, so in the first row, in the first element, I put A, and in the first row and in the second element, I put positive B, and vice versa. On the then in the next row I put minus B here and plus A here, and this matches my specification. This matches my the way that I write this particular complex number. Okay, so I think the point is, the thing that I was worried about is, can I call this I, the B minus B? If this was 0, 0, B minus B, can I call this I? And yes, I can. It turns out if I call this I, then I have to call the complex conjugate, which is a minus B here and a plus B here. So when I set up my conjugate, the B has to be here, and so the minus B has to be here, and the plus B has to be here. Otherwise, everything works the same. So I can call this I if I want to, and then the conjugate becomes the conjugate identity becomes the negative I. So minus B plus B, as is shown right here. So the real problem has more to do with convention and less to do with whether this is minus or plus or minus. I can define my convention as long as I'm consistent. I can call this I, and so it's more about the convention. And so I'm going to show you my convention, and I'm going to show you that it works out perfectly fine. So this is from Eric Dollard's paper. This is the one slide, figure 5, where he shows the resistance and the reactance and the impedance. So the resistance is on the positive X. So positive X goes to the right and positive Y goes up. And so positive X is the positive real axis, and the positive Y is the positive imaginary direction. And so that's how I've set up my software. I set up my software so that positive X goes to the right, positive Y goes up, and of course there is a hidden Z which you can't see, but the Z is pointing towards me. So this is my coordinate system here that I'm using, which matches the standard that Eric Dollard had in his paper and that most people use for complex numbers. So in this version of the software, I am using complex numbers only. And so what I have here is I placed a little sphere in the positive X direction. And what I am going to do is I'm going to apply what I am calling positive I. I'm calling I in my coordinate system, where the positive 1 is in the upper right corner and the negative 1 is in the lower left corner. And so what I'm going to do is I'm going to apply I'm going to apply that matrix to this sphere. And as you can see, I clicked once and it went from the positive axis, positive x to positive y. And so it did a negative 90-degree counterclockwise 90-degree rotation, exactly as we would expect I to do. So let's do it again. Now it goes to the negative x direction, and I'm going to do it one more time, and now it's going to the negative y direction, and one more time, and it's back to x. It's back to the positive x direction. And so, so this parameter here, my setup of the complex matrix for the 2x2 complex matrix for the let's say positive identity is has b in the upper right corner and minus b in the lower left corner. And so this is functionally identical to I. My software rotates around this axis, around the z-axis. It's rotating around the axis that's invisible, which is the z. You can see it, though. I can show you. There it is right there. But when you reset it, it's pointing towards me. This is a, for the record, this is a right-handed system, a right coordinate system, right-handed coordinate system, which is used very often in medical imaging. And so the way I try to recognize a right-hand coordinate system is I point my index finger in the direction of positive x, and then I point my second finger, the one that you use for saying bad things to people. You take that finger and you point it in the direction of positive y, and when you do that, your thumb is going to point in the direction of positive z. Okay, so that's how I define the right-handed coordinate system. It's used in medical imaging, so this is the coordinate system that I choose. And when I use a right-handed coordinate system and I use my definition of I, the rotation is counterclockwise from positive x to positive y to minus x to minus y, and back to positive y, exactly as I said before, exactly as we expect I to do. So now what I'm going to do is, instead of passing in the identity matrix, instead of the positive I identity matrix, I am going to switch to polar coordinates, and I am going to pass in an angle. So I'm going to disable this line of code, and I'm going to enable this line of code, and now I'm passing in the cosine of the angle and the sine of the angle. And of course this is going to call the setup function is going to set up this this 2x2 matrix, and it's going to put it into the matrix, where are we here? It's going to put it into the rotation matrix. And so this is how it works. This is how the code works. You put your point into a complex 2x2 matrix. I call it a point matrix. Then I take the angle that I want to it to spin, and I take the cosine of the angle and the sine of the angle, and I put that into a matrix called rotation. And then I just multiply those two rotations together. I will multiply the point matrix by the rotation. So this is rotating the point. And so let's run this. Okay, so now I am going to be rotating by 10 degrees instead of, or minus 10 degrees. It's going to look like it's going to go counterclockwise by 10-degree increments instead of 90-degree increments like it did with this line of code enabled here. So let's wait for this to come up. I'm going to add my point. There it is right there. And now I'm going to spin. Okay, so as you can see, it is spinning counterclockwise, but now I am only going 10 degrees at a time. So that's how you get, that's how you fine tune the quaternions. Instead of passing in ones and zeros, you pass in the angle, Euler angles, basically, the cosine and the sine. And so here I'm just going to show you, so I'm going by 10-degree increments. So when I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, I'm going 90 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 90 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, so when you use the Euler angles, when you use the angles, these are Euler angles, when you plug those in instead of the matrix, so the identity matrix can only go 90 degrees one way or another depending on how you set this up. But when you use the Euler angles, you can go any angle you want. So as you can see, complex numbers, when implemented as a 2 by 2 matrix, function exactly as you would expect complex numbers to behave. Real numbers and imaginary numbers together, this is how you would expect them to behave. So this is an alternate implementation of complex numbers that is functionally identical to complex numbers, but we never really need to invoke the labels of real and imaginary, because in a 2 by 2 matrix, all the values are real in the truest sense of the word. And basically, you are just talking about addition and multiplication. We're doing addition and multiplication, and no algebra. Okay, so this, I was able to do everything that complex numbers can do in my code without invoking any algebra whatsoever. So this is a nice solution for people that don't want to learn algebra, that don't know algebra, but know how to add and multiply. And, you know, they would have to learn how to add and multiply, you know, 2 by 2 matrices or 4 by 4 matrices, but that is just a game compared to the language of the symbolic language of algebra, which confounds people for the most part. So now we're going to move on to setting up the quaternion. So doing complex numbers and doing quaternions in this fashion is functionally basically identical. Okay, so the way you approach it is basically identical, only you have a bigger matrix to deal with. And so this is the quaternion that I derived, that I showed in my previous videos. This is the one that I found using the code to try and find the identities for the quaternion, the IJK, and this is what I found. And I like this one because it's got the forward diagonal has the same sense, and the backward diagonal has the inverse sense or the opposite sense. And so the big quaternion is, for all intents and purposes, a complex number in itself. But there are other quaternions. Okay. And I'll talk about that in a bit, but it's really not important. It turns out, as I discovered through my experimenting, it doesn't matter which one you use, as long as you use it consistently. So all of the quaternions I found, I think I tried 3 different configurations, and they all basically work the same. So as long as you just pick one and stick with it, it doesn't really matter. And so there is another quaternion I found in the literature, and I implemented it, and sure enough, it behaves exactly the same. And so this is, I refer to this as the left chiral quaternion, or they referred to it as the left chiral quaternion, the article that I found this in. And so the reason I like this one is, if you remember before with the complex numbers, I liked this configuration because The answer after I do the multiplication are in the top row. Okay, so with my matrix, with the matrix that I showed you last time, the top row is A, B, D, and C. So when I use this matrix, I have to be careful to choose the right element from my answer array, from my the top row of the answer quaternion, the result. I have to remember to swap C and D, and so that is a little annoying. And so the other quaternion, the left chiral quaternion that I found in an article, actually might be a better one to use, because you've got A, B, C, D in the top row, and so my result that when I'm debugging is A, B, C, D. I'm less likely to get confused. So I am probably going to end up using this quaternion in my specification. Even though it doesn't satisfy all my criteria, the forward diagonal does not have the same sense, and the backward diagonal does not doesn't have the opposite sense. So, but this functions perfectly well as a quaternion. It's got all of the features of a quaternion, and so I could just as easily use this one as this one. And so it doesn't really matter as long as I'm consistent and under the hood, as long as when I build my class that does quaternions, as long as I know what I'm doing, then it shouldn't be a problem. But due to the fact that I'm easily confused, I think I might switch to this quaternion. So here is my code. First, what I do is I set up my point into the quaternion object, into the quaternion matrix, as I show here. Okay, then I set up, I need to have a rotation quaternion and a conjugate of the rotation quaternion. So I set those two up. I have set up quaternion, and I actually have a function, which I'll show you here, where I set up the conjugate. So you can see that the quaternion matrix, it looks like this, and the conjugate is all of the imaginary components are negated. Okay, and so I set it up, and then I do two multiplications. I multiply the quaternion, I multiply the point with the rotation, get a result, and then I multiply the result with the conjugate to get result 2. Okay, to get result 2. Then I pull my result out of the matrix, and since I'm using my normal matrix, since I'm using this one, I have to swap C and D, which is why I am doing 1, 3, 2 instead of 1, 2, 3, but that's neither here nor there. Let's run this program and see what happens. So here we have our usual sphere in the positive x direction. If you look at our coordinate system here, you can see that my sphere is in the positive x direction. And now when I click the spin button, when I click the button to make it to activate the two quaternions, the rotation one and the conjugate one, you get the counterclockwise motion about the vector. And so in my code, I made the axis in the direction of positive z, and when I reset my camera, positive z points towards me. And so here, this is this quaternion is behaving exactly as specified. So I am moving 10 degrees, 1, 2, 3, 4, 5, 6, 7, 8, 9, gets me to 90 degrees, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 gets me back to 90, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 90 degrees gets me back to where I started. And so, so this code here, this little chunk of code here, where I take the point, right? I take the point and put it into a 4x4 matrix, and then I take the rotation and put it into a 4x4 matrix, and I take the conjugate and put it into the 4x4 matrix, and then I multiply the point, the rotation matrix by the point, and then the final result of that by the conjugate. Now this is a bit of a rigmarole. You also notice that I have to pass in the angle divided by 2. But regardless, this is the standard approach to the implementing quaternions, and this is a standard quaternion setup where each component is the cos and the 3 sines are you pass in the angle divided by 2. Okay, so this is standard quaternion approach. This is a standard quaternion approach. And the other part of it is where you multiply the quaternion, the rotation quaternion on the left side of the point, and the conjugate quaternion on the right side. So like I said, this is a bit of a rigmarole to get to the result, to get my point out of result 2. But this is basically, this is how it's historically been done using quaternions. So now I'm going to change my vector to an arbitrary vector. I'm going to have it pointing 30 degrees, I'm going to have the end of my vector pointing at 30, 30, 30. So this is going to define my vector. So let's run this. Okay, there's my point. There is my sphere pointing in the positive x direction as usual. Okay, just so you can see my axis here. And now I'm going to spin, although now it is spinning about a different axis. Okay, it's spinning about, it looks almost like an elliptical orbit. It is spinning about a different axis. And so what I'm going to do is I'm going to rotate my coordinate system so you can see what's going on. And so basically what's happening is it is spinning in an axis that is not normal to my 3 coordinate axis of my coordinate system here. Okay, it's at a 45-degree angle basically to the other axes. Okay, so you can see that. So what I do here is I've got a central point. This is my 0, 0, 0 of my coordinate system. This is my vector. Okay, so this is if you drew a line from here to here or put an arrow here, this would be my vector. And so when I line up this circle with this circle, it's just a little trick. It's easy to draw spheres. I just use spheres because they're easy. When I line up the spheres, then I know I am normal to this vector with respect to the screen. And so you can see that it is a nice circular orbit around this new vector that I created. Okay, so so this quaternion seems to be functioning perfectly fine, perfectly well as a quaternion. I can't really see any problem with it. When in a right-handed coordinate system, when the vector is pointing towards me, okay, it's always going to seem like a counterclockwise rotation. But if I take the vector, I'm going to put it on the other side, it's going around in a circle. Now the vector is on the other side of the green here. Okay, so now the vector is pointing away from me, it's pointing into the screen, and now it's going to look like a clockwise rotation. So this is another example of clockwise versus counterclockwise. Do imaginary numbers spin things clockwise or counterclockwise? It really depends on your point of view. It depends on which way the vector is pointing. And so there, now I'm back to clockwise rotation. Okay, so these quaternions are behaving exactly as expected using the standard protocol of taking the complex conjugate and doing these two multiplications as they do as described in this paper. So now what I'm going to do is I'm going to show you what happens when I use multiple points. Okay, so these are points that are both in plane and out of plane. The 0, 0, 0 is the green dot here. So the plane of rotation would be, you know, something like that. So now let's do one spin. Okay, what I'm going to do first is I'm going to show you what the spins look like when they're, you know, when the axis is pointing towards me. So as you can see, we're getting our usual counterclockwise rotation at 10-degree intervals. So 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see that it is rotating 90 degrees when I click my spin button 10 times. So now what we're going to do is we're going to look out of plane. So now the axis is pointing up. And as you can see, all the points are orbiting this axis quite nicely. So the Quaternions are working as specified. If this was a 3D model with a bunch of triangles making up the 3D model, you would apply this rotation, this Quaternion to each vertex of the triangle, and your model, your 3D model, would rotate about this axis. And so that's how 3D graphics works. Quaternions work quite nicely for orbiting, rotating 3D objects in a 3D coordinate system. In fact, the camera view, which you see here where I'm manipulating the camera. There's the coordinate system of the camera. It likely also uses Quaternions. But here's the thing. In the previous iteration of this video, I made a mistake. And I'm going to explain that to you. So here's my code for rotating the points. Okay, so for each point in my list, I set up the point, and I set up the rotation matrix and the conjugate matrix. I multiply the point by the rotation matrix, and I multiply the point by the conjugate matrix. And then I pull out the point from the result and display it in my view. So what I said in the previous video was that I could get rid of this, and therefore I could get rid of this. And I'm going to put this into result 2, and I'm also going to remove the divide by 2's. So this is what I claimed I could do using the 4x4 matrix version of Quaternions. Okay, so this is more like what I did with the complex numbers, where I took the point, multiplied it by the complex number. Here I'm multiplying it by the Quaternion rotation matrix, and then pulling out the point. So let's see what happens when I do this. Just give it a second to compile. Okay, so here are my points, and I'm going to do one spin so I can see my axis. And so I'm going to start by looking, so the axis is pointing towards me. 1, 2, 3, 4, 5, 6, 7, 8, 9. It seems to be working perfectly well. But now what I'm going to do is I'm going to show you what it looks like when off axis. So what you see is the points are spreading apart, coming together, spreading apart, coming together, spreading apart, coming together. So when they come together, they are all on one plane. So this is strange behavior. Obviously, it's not the correct behavior. It's not the behavior that we expect for if we want to rotate a 3D model. And so I thank you, Mike, for pointing this out to me. I was wrong about that. You do need the, okay, let's go back to my code here. You do need the, you need the divide by 2's. you need the conjugate matrix. You need the conjugate 4x4 matrix. And so I apologize for that mistake. I didn't do my due diligence to check to see if the outer plane was working. I just assumed it was working. And making assumptions when you're doing this kind of thing is not correct. It's not right. And so we shouldn't be making assumptions at any point, and no scientist should be making any assumptions at any point in their experiments. And so so that is fine. These quaternions with the 4x4 matrix, the point I wanted to make really is that the 4x4 matrix version of quaternions is functionally identical to the standard implementation of quaternions. And no, I don't expect this to be more efficient. I expect it to be less efficient because we're doing more multiplies. We're multiplying, a 4x4 matrix by a 4x4 matrix, and we're doing that twice. And so, but that wasn't the point I was trying to make. The point I was trying to make was that the 4x4 matrix is functionally identical to quaternions, and in the complex numbers, the 2x2 matrix is functionally identical to the complex numbers. So next, what I'm going to do is I'm going to show you how I apply quaternions to the Mandelbrot set. And of course, I've been talking about this, doing this for a while, showing you this for a while. And so I just want to point out that in order to do this, I have to do a really low resolution Mandelbrot set because I have to calculate four-dimensional numbers. So if my width and height are 100, then my volume is going to be 100 times 100 times 100 times 100. And so if I go much bigger than this, number one, it's going to take forever to generate, and number two, it's going to take up a lot of memory. So first I'm going to show you the code that I wrote to generate the Quaternion Mandelbrot set. First we need to look at the formula for the Quaternion, which is AR plus BI plus CJ plus DK. And so there's one real component and three imaginary components. And the equation we're going to use for the Mandelbrot set is Z equals Z squared plus seed plus seed. So my C, my complex number, is a seed, and that gets seeded into the iteration process for each point that I analyze on the complex plane. So here are my three variables. I have a variable, these are my three matrices, my three 4x4 matrices that I'm using as quaternions. I've got my seed matrix, I've got an intermediate matrix that I need for the calculation, and I've got the Z. Okay, so this is just these are just the three matrices that I need to generate the Mandelbrot set. Next thing I want to show you, in order to do the Quaternion version of the Mandelbrot set, I need four next loops. I need four loops. That's hard to say. I need four loops in order to generate the four-dimensional complex Mandelbrot set. And so you can see there is a for loop for the A, one for the B, one for the C, and one for the D. So what I'm doing is I'm integrating through the real and the four imaginary components of the complex space, of the Quaternion space. Okay, and then the next thing we need to do is we need to set up the matrices that I defined previously. So I have a function called set up Quaternion, which I showed you before, but we'll just have a little peek here. Hopefully it'll come up quickly. There it is here. So I set up the seed point into my Quaternion matrix. Okay, and I also initialize Z to the Quaternion matrix to the same point that the seed point is. So Z starts at seed. Z starts at C. It always does. So Z starts at 0, and then the first iteration it gets transformed into C. So you might as well start Z at C. So that's what I do. I save one iteration by doing that. Then once we have those set up, then we do the iteration. Now we iterate. So the iteration loop is right here. I use a while loop to do my iteration, and I iterate until I am done. And so I have max iterations set to 1000, but I'm going to reduce that to 100. So for the low resolution Quaternion Mandelbrot that I'm generating of 100 by 100 by 100 by 100, I don't need 1000 iterations per pixel. I only really need 100, and this is going to save a significant amount of time. So then what I do in the iteration loop is I take the matrix Z and I use my multiply matrix function. I multiply Z by Z, which is really Z squared, and I put that into a temporary matrix. Then I use my add matrix function to add the original seed value, which is C. The C part of Z equals Z squared plus C. This is the point on the complex plane. And so I add the seed back to my temporary value and put that back into Z. Okay, so this is Z squared plus C in these two lines of code right here. Then what I do is I pull out the result from Z and I pull out the top row, which is, you can see here, 0, 1, 3, 2, because I'm using my matrix that has C and D swapped. Okay. Then I calculate the distance using Pythagorean theorem. Only now there are, with Quaternions, there are 4 components, A squared plus B squared plus C squared plus D squared. And this is measuring the distance from the origin, from the 0, 0 of the complex plane. So if this distance is greater than the escape radius, which I'd previously set up to be 2, so the 2.0 radius, the 2.0 distance from the 0, 0 of the complex plane is the escape radius, is the escape distance, the escape radius of the Mandelbrot set. And this is the case for both the complex version, the 2x2 matrix version, and the Quaternion 4x4 matrix version. And so if it escapes and we have done, at least one iteration, then I'm done. I can say my iteration is complete. And then what I do is I assign a color based on the number of iterations. So this is the standard technique. You iterate. If it escapes after 10 iterations, you give it the color blue, and if it escapes after 20 iterations, you give it the color red, or something like that. So I have a color array, actually 3 color arrays that I set up to colorize the Mandelbrot set. And so if it doesn't escape, then we increment the iterations, and then we test to make sure we haven't exceeded our max iterations, which I set to 100. Okay, so if it exceeds the max iterations, then I stop. Again, I say iteration complete, we're done. And I assign a color to the non-escaping points, which traditionally are painted black, but I am painting it dark blue just because I think it looks a little nicer. So that's about it. That's about it. Okay, then when I'm done iterating, then I plot my point. I plot my color in the position that I'm analyzing in the complex space, in the Quaternion space, whatever point that is. I colorize it, and that's a bunch of stuff going on down here, which I won't waste your time with. This is really the guts of it right here. This is the guts of it. This is Z equals Z squared plus C using matrix multiply. I'm using 4x4 matrices for my Quaternions, and I am generating the Mandelbrot set. So here are the 2 volumes that I generated. This one is R, I, and J. J is in this direction. And this one is I, J, and K. K is in this direction. So you can see what I'm generating here is actually a three-dimensional volume, which you can slice and dice in any orientation that you like. So as you can see, I can orient my slice planes. I've shown this before in other videos with other things that I've put into this 3D cube. This is in my work. We use this for displaying MRI images and three-dimensional ultrasound images, but I like to use it as an alternate visualization tool for some of my other my independent research projects. And so as you can see, the real component, so this is basically just the two-dimensional complex plane right here. So this is the real component, and this is the one of the imaginary components. It doesn't matter which one because they're all exactly the same. And so if I slice in from this way, you will see there is the Mandelbrot set again. Okay, so what the Quaternion does is it gives me three. So basically what I'm trying to tell you is that Ri, okay, Rj, the real and the j, and Rk. So if this was the real component and this was k, it would look exactly the same. And it doesn't matter where I spin this on my about the real axis. So when I spin this about the real axis, it's all Mandelbrot set. It's all just the two-dimensional Mandelbrot set. Okay, so so here on the right, I have only the imaginary components. And as you can see, this is a it generates just a spherical geometry. This is a sphere. It's not nearly as interesting as the Mandelbrot set. And what this shows, okay, what this shows is that all of the imaginary components are functionally identical to each other. Basically, they're just in other orthogonal directions, although they point in the three orthogonal directions. Okay, you don't get anything new. You don't get any novelty, and you don't get any of the Mandelbrot fractal patterns, although, you know, if I zoomed into here, I might see something interesting, but you're going to get a spherical symmetry. You can see a spherical symmetry, and so that is how this is working. And so the what this tells me is the Quaternions don't add any novelty to the fractal pattern. Okay, so, you know, there's no new patterns in here. There's nothing sort of that we haven't seen before. And so, although it's very interesting, it's also, when I first implemented this around 10 years ago, it was also a little disappointing because I thought maybe there might be some novelty in the Quaternion representation of the Mandelbrot set. But really, it's just Ri, okay, Rj, and Rk, and the R and the K component would look exactly the same. Right. So, so this is what I wanted to show you. Again, you know, it might be a little disappointing that there isn't something new going on here, but what this tells me is that the complex plane is the novelty. The two-dimensional complex plane is special. There's something special about it. It is powerful. It is, so Quaternions are really just the, you know, three-dimensional extension of complex numbers. They, as I showed you before, they are complex numbers under the hood, and it is really the complex number that is special. Okay, the complex number, the two-dimensional complex number is the thing, is that which is special. And so I've always had this intuition. In fact, I was hoping, I was secretly hoping that I would be able to do everything that I wanted to do in terms of my cosmology using only two-dimensional complex numbers. And it turns out this is true. So for some of the projects that I worked on in the past, it turns out that I only need complex numbers. I can do it, all of my calculations with only complex numbers, as I showed you in some of my videos on Eric Dollard's paper, that I can implement his calculations for electronic component using only complex numbers. I don't need quaternions for that. I also recently discovered and tested this out and realized that I can do the Yonel didn't use ether along the wire, his electrogen and ether circulation about the wire, which I refer to as the ether circulation model, using complex numbers only. I don't need quaternions to do this. My previous implementation, I used a 4x4 matrix that had a 3x3 rotation matrix built in and a translation built in. But it turns out I don't need that either. I can do this. I did this. I tested it to make sure it could be done. And so this implementation here, I'm just showing one plane through the wire, but this was done using only two-dimensional complex numbers. And so complex numbers, the two-dimensional complex numbers are very powerful. So what I want to do is re-implement all of Yonel's work using complex numbers only. And I also know that I can re-implement all of my Taurus knot work that I did in the past using complex numbers only. And it's super simple. I did it in my head and I went, oh, that is way easier than, the way I did it before. And this is actually way easier than the way I did it before. In terms of lines of code, it's less lines of code. Whether it's more efficient or not, I don't know. It's probably not. Well, actually, for this, it might actually be more efficient because I had to jump through hoops to get this to work using the standard tools that I usually use. And so this was very easy to implement. You just have to be in the right mindset to. So here is the circular loop of wire, and as you can see, I can do, so this is not animated yet, but as you can see, I've got this happening both in plane and out of plane, and I've got circles upon circles upon circles. And so when you have that kind of a, so I've got the big circle, and each of these is, circulates around the wire. Not circulates, but, I'm showing all of the positions around the wire. And then, of course, each of the ether circulations is a circle in itself. So when you have circles upon circles upon circles, like epicycles, I guess you could say, then I can do this with complex numbers only. And so this is a nice way of doing it, because not only is it simple, but it also proves that complex numbers are special. Complex numbers are super powerful, and if you use them correctly, you can do some really interesting things. And so, the goal of my research was to find I call it the math of least resistance. Okay, so in my mind, the real genius isn't, who can do the most math. Okay, the real genius isn't who can learn the most math in the shortest period of time, but the real genius is who can do the most with the least amount of math. And so I can do with complex numbers, just two-dimensional complex numbers, and using the 2x2 matrix format, which eliminates the need for the terms real and imaginary, because they're just two-dimensional numbers with, forward diagonal and backward diagonal having different functions. So Using complex numbers alone, I can do so much. Okay, I can generate all these fractals. I can generate the Mandelbrot set. I can generate the Julia set. I can generate the Buddhabrot and what I call the Bubblebrot. I can also generate all of these crazy trajectories. Okay, these trajectories, which like these guys here. Let me show you, right? This is also part of the Mandelbrot set, the two-dimensional complex plane version of the Mandelbrot set. And so I can generate so many different, images using just the complex plane and z equals z squared plus c. All of these images were done using z equals z squared plus c and the Mandelbrot set. What else have I got here? So many different Buddhabrot images, right? Beautiful, beautiful Buddhabrot images. These guys here, these are also Mandelbrot trajectories generated from points in the complex plane as iterated through the function z equals z squared plus c. And these were also done using the Mandelbrot set and the complex numbers and this crazy video here, which I may have shown you before. And so let's just have a look at this quickly. It gets a little crazy as this goes on. Yeah, so there, now we got some chaos going on. And so, but not only that, but I can re-implement Yarnell-Dinyu's ether around the wire. When you have current flowing through the wire, it creates ether circulation and around the wire. And these here would be the magnetic field lines. Okay, what you see here. And so complex numbers can be used to help understand magnetism, to help understand electricity, all of the symbolic language that Eric Dollard is trying to develop with his algebraic symbolic language and his versors can easily be done with complex numbers alone. I don't need quaternions for that. I only need the 2x2 matrix version of complex numbers, which it doesn't have to be the 2x2 matrix version of complex numbers, but that is what I am going to be using from now on. And so it's so powerful. I'm sure it could be used in quantum mechanics. I'm sure it could be used anywhere where you use complex numbers. I have a feeling that the 2x2 matrix version of the complex numbers is going to give a little bit of insight into those topics, okay? Because the forward diagonal is the scalar and the backward diagonal is the rotar, okay? It rotates things, and between those two components of the 2x2 matrix, you can do all this stuff, right? You can do all this stuff. And so that's all I'm going to say for now. Here are a few more of my planetary nebula images. Yeah. So that is all I'm going to say for now. Complex numbers are cool and very powerful. And that is the message that I actually wanted to get to Eric Dollard when I talked to him that fateful day. I wanted him to know that, first of all, he's on the right track, but that his symbolic language could easily be implemented as the 2x2 matrix version of the complex numbers. And so that's what I was trying, that was the message I was trying to get to him when we had our conversation. And so I hope he watches this video. I hope he sees what I'm trying to say here. And, maybe, I'm going to continue to work to study his work and to see if I can further implement his language into the code base that I'm developing for my complex number system. So I hope you are all having a great day, and well, I'll be back.